the next thing I'm going to do is I'm going to find another vector that's in this plane of rotation that also gets rotated by 60 degrees. And I want it to be a perpendicular vector because it's a 2D plane of rotation. If I can find one vector, I did, SW60, I want to find like another vector that's at 90 degrees. And then it'll be like, cool, I have like a little basis for this two-dimensional plane of rotation. And again, I'll just tell you what it is. So here's a claim. A perpendicular vector, perpendicular to this, to in the same 2D plane of rotation is this one, which I'll call SW 60 degrees perp, bottom. And it's literally like the exact same thing as SW60, except that you start with the vertical vector rather than starting with the horizontal vector. So SW is just like, oh, you start horizontal vector and then you rotate it clockwise by 60 degrees. This one is just going to start at up. Now it's even more like a clock. Like you start at like noon or whatever, and then you go to 60 degrees, 2 o'clock? Yeah. Oh, great. So you go, oh, I should have had this in my mind the whole time. I know where 2 o'clock is. OK, so cool. So you go to like 2 o'clock, and then 4 o'clock. Oh, I should have said this all along. 6 o'clock, 8 o'clock, 10 o'clock. Oh, wow. So great. Why didn't I say that? You can even, like, this one's like even nicer. You can even sort of see it like kind of, I don't know, going around by 60 degrees clockwise. Oh, great. Yeah. OK. So let's talk about this other vector. A lot of the things about it are kind of clear. So in the exact same way that, well, let's see. Let's first check that this thing is actually perpendicular to that thing. And we can easily check it because it's very similar to this. Like if you wanted to check that this is perpendicular to this, that's like checking that the dot product of this vector and this vector is 0. How would you compute the dot product of this vector and this vector? Well, you'd write them out the same. Like it's almost the same thing. This is like SW60. And we would just imagine writing this one down here. And then the overall dot product, maybe up to this factor, is like the dot product of the first columns and the second columns and the third columns and the fourth, fifth, and sixth. But a similar thing happens, right? Like the angle between the first columns is 90, so that dot product is 0. These are also perpendicular, so the dot product is 0. Dot product 0, 0, 0, 0. So the sum of all the dot products is 0, so the overall dot product is 0. So indeed, these two vectors are perpendicular. And there's one more thing that we need to check, which is that this vector is in the same two-dimensional plane of rotation as this one. OK, so we have this vector. You apply r. It starts rotating around the plane. And we need to check that this vector is in that same plane. So how can we check that? It'll be like a similar argument. So we're going to check that this SW perp is a linear combination of some of the rotations of SW. So we need to show that SW perp is a linear combination of all these vectors in the plane, like SW60, R applied to SW60, R applied twice to SW60, and so forth. Whoa. And how can we do that? Well, luckily we have some of these on the board. our SW60 is this purple one. So let's use that. So let's use this purple one. This purple one is pointing like this. I guess it's like 2 o'clock and, no, 1, how did I get to 1 o'clock? What? Oh yeah, that makes sense. It's like 1 o'clock, it's the odds, 3 o'clock, and 5 o'clock, 7 o'clock, 9 o'clock, and 11 o'clock. And let's also use the blue one, I think. Yeah, let's use the blue one. And yeah, the blue one over here, the third one, that's easy. It's like 3 o'clock. So then, no. Wait, do we want the blue one? Oh, no, we want the blue one over here. This is there. 3 o'clock, 5 o'clock, 7 o'clock, 9 o'clock, 11 o'clock, and 1 o'clock. And now, hopefully, you can at least visually see again, like the black vector of this guy is like exactly sandwiched between the blue and the purple ones. So here, again, the black vector, which is SW perp, is, if we take the average of these two, it's parallel to SW perp. Okay, so indeed, like this one is like just like an equal linear combination of these two rotations. Okay, so that checks off the fact that this is, we saw that it was perpendicular, and we saw now that it's in the same 2D plane. Okay. Good. So let me summarize where we are. Because we're almost done the main part of this day of checking. So the summary so far is we found one, well, let's say perpendicular basis for one plane of rotation for R, and it's by 60 degrees. Okay, and it's like SW 60 degrees and this SW perp 60 degrees. Okay, so we've like done one piece of the task of finding all the planes of rotation. And let me just say, okay, we did it with 60 degrees just to make it a little bit more concrete, but like generally, we can, for general L, you can define the two 2L dimensional vectors, like steering wheel sub theta and steering wheel perp sub theta, for theta being a 1 over L fraction of the circle. Okay, so what was going on with 60 degrees here? It was like when L was 6, we were talking about 1/6 of the circle. So in general, everything we did like generalizes to general L, not just 6. And these will be length 2L vectors consisting of like L little two-dimensional columns. And like this will consist of, the horizontal vector, and then you like go by 1/11 of the circle, 2L, 3L, 4L, 5L, etc. Okay. So we worked pretty hard, but the good news is all this work can be reused going forward for finding the other planes. Because what you really need to like imagine now is in this whole story, getting this one plane of rotation, what role did the angle 60 degrees play? Like, at the very beginning, I just wrote down this like, vector, the steering wheel vector that had like L columns in it. And I just said like by fiat, the first one's horizontal, and then we're going to go, each step around is going to move you 60 degrees. What was up with 60 degrees there? Well, we needed it to have the property that like when you did 60 degrees, 60 degrees, 60, 60, 60, and one more 60, you should get back to the beginning. We needed that so that this really had the property that like the doing R cyclically shifting these 2D vectors was the got you back to yourself after you did it L times. But everything we did will all work the same as long as theta is an angle with the property that if you rotate by it L times, you get back to where you start. So this is like an observation. Maybe you have to like go over the movie in your head of everything we've done, but like everything is the same. So long as like rotating by theta L times is equivalent to doing nothing. But there's more angles than just 60 degrees, or 1 over L tau, that have this property. Like 2 over L tau also has this property. If you do that L times, yeah, eventually you go around the circle twice, but you get back to where you started. So also the same for theta being 2 over L of a circle, 3 over L of a circle, L minus 1 Lths of a circle, and actually also 0. So for all of these L different angles, we can define like a steering wheel for that and its perpendicular one. And we'll get the same conclusion. So we'll get like a plane of rotation for all of them. So let me write that over here. Actually, let me just illustrate a little bit over here too, what I'm talking about in the case of 6. So like I'm saying, we can also define steering wheel 120 degrees, and that looks like starts horizontally, and then it goes by 120 degrees. So it goes here, here, back to here, 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 and then it'll go back to here. Okay, and this is another state that starts vertically. And it goes 120, 120, 120, 120, 120. So like these two, these are a basis for a plane of rotation for R of angle 120 degrees, which in this context is like 2 over L, fraction of the circle. Because you just like repeat everything we did for this picture as well. Okay. So we can conclude that we sort of, well, except for one more tiny detail, which I do have to get to, we found all the planes of rotation of R. Because R is in 2L dimensions, and we found L different planes of rotation, each of which is 2-dimensional. So that's like all the dimensions. So the conclusion for this 2L dimensional operator, or unitary, I should say, R, we found L different 2D planes of rotation with angles And I'll say in parentheses, as promised, 0 fraction of the circle, 1 over L fraction of the circle, 2 over L fraction of the circle, etc. L minus 1 over L fraction of the circle. Okay. So there's still a little bit more to do. So there's actually one aspect of this we didn't quite yet check that we should still check, which is that, we found these L different planes of rotation. Now these are supposed to be like mutually perpendicular planes of rotation. And that's like one little property we didn't check. We didn't check that like this plane is perpendicular to the plane with SW60, and it's perpendicular to the plane with 240 and 180 and so forth. Let me write this down, because I think a lot happened in this lecture, so I think I'll not do one more mathematical check now, but we'll save it for next time. But still to check, so we'll do this next time. One, these planes are perpendicular to each other. And we will need this fact. But again, it's the sort of thing where like maybe it feels like intuitive, or like, you'd say to yourself, OK, I'm sure it's true. Like everything's been working out fine so far. One other like extreme minor technicality, which I'll now like, you can just turn your ears off and I'll like read this into the camera for the record. What are we going to do with this? We're going to do rotation estimation on this R. You may remember, or you may have blocked it from your mind, which I recommend. Then when we talked about rotation estimation, the final lecture about it, we were like, there's this glitch. There's this glitch that has to do with like, sometimes the algorithm needs to like do this like offset rotation by like 90 degrees or like 180 degrees or something to deal with this like annoying issue. And so the algorithm needs to be able to like do a 90-degree rotation in whatever plane is, this vector is rotating in. And that seemed difficult because we're like, what if we don't even know the plane? How are we going to like do this offset rotation of 90 degrees if we don't even know the plane? But in this beautiful setup, we can just easily fix this glitch because no matter which of these, SW states we're in, the algorithm itself knows how to do a rotation by 90 degrees to the state because it just has to do it on the B qubit. Like it can rotate the SW by like any amount in its plane of rotation just by doing that rotation on the B qubit. Because that exactly will rotate each of these columns by the desired amount. And thereby, we can get around that glitch because of the beautiful nature of the setup we're in. OK, that was like some fine print for the record. OK, let's go back to where we were talking about. So next time, because I don't want to do it in 2 minutes, we'll check that these planes are perpendicular. And so then we can truly say, like, OK, we truly did it. We found precisely all the perpendicular two-dimensional planes of rotation for this operator R. And therefore, we kind of should be able to know exactly what happens when you do rotation estimation with R. And it's kind of like an annoying situation where we're like, as the algorithm, we say to ourselves, oh boy, if we could just like make our qubits, A1 through AN and B, into this steering wheel 60 state, that'd be so great. We'd make them into this state. We'd be like, that's our start vector. We'll do rotation estimation with R and that start vector. The angle of rotation is 60 degrees, and so we'll just learn that. We'll learn like, as many digits as we want of that. And so it'll be exactly like the algorithm would learn, like 1 over L tau. And then it would divide by tau, which is 2 pi, and it would take the reciprocal, and it would find L. Be like, great, we did it. Or if it could somehow make the steering wheel state with like 2 over L tau, it'd be like, this is also fine. I'll make that state. That'll be my start vector. I'll do rotation estimation. I'll learn all the digits of this fraction, 2 over L tau. I'll divide by tau. I'll take the reciprocal. I'll divide by 2 or whatever, and I'll figure out L. But sadly, the algorithm doesn't know how to make any of these states. I mean, maybe it's not clear, but like, there's just like no way the algorithm can figure out how to make any of these steering wheel states. So it seems like we did all this work for like, I don't know, unclear benefit. Like we have like all these like two-dimensional planes of rotation. I can't really draw them. You know, where we're rotating by 1 over L tau, 2 over L tau, 3 over L tau. And we can't seem to find a vector in any of them. But what we'll do next time when we wrap it up is we'll show there's like one vector that the algorithm can make that's like in this span of everything. It's what we said would be start vector all along, which is just, I don't know, the vector that stands for 1. And then maybe you have to throw in a qubit for b. And what we'll show next time is two things. We'll show this vector, although it's not in any of these planes, it's got kind of like an equal amount of components on each of these planes. In fact, this vector is literally the average of all the different steering wheel vectors, an equal average of all of them. That's not too hard to compute. And so like this starting vector is kind of like an equal superposition of all the possible starting vectors. And then the very last thing we'll show is that, like, well, if you don't plug in a vector in one of the planes and do rotation estimation, but like you plug in like a vector which is an equal superposition, has an equal superposition of like a piece in each one of these planes, and then you do rotation estimation, we'll show that you just get back equally likely an approximation of 1 over L or 2 over L or 3 over L or 4 over L. And this was like the clue that we said would allow us to finish the job. We'll get back a randomly chosen fraction of the form k over L tau. And that's what we'll do next time on Tuesday.